Okay. Okay, so we'll start. Today we'll discuss important topic of key exchanges and very important algorithm that's called Diffie Hellman algorithm. Okay. The references are the same. We'll continue to use contents provided by University of California, Berkeley. Then these books, these are very good books. Yeah, a lot of video lectures are available on topic. If you want, you can go through it. In fact, there is a video lecture also available from the University of Berkeley, University of California at Berkeley, right? Okay. All right. Please feel free to ask me a question because today's topic is little complex. Because a lot of mathematics will not go into details of the mathematics because this is a full topic in itself will require few hours. So we will just try to understand the concepts. We will not go into the mathematics. Okay. Usually this topic is taught in as a separate subject. It's called modular mathematics, or sometimes it's also covered in the theory of algorithm course. Okay, because it has theoretical computer science and mathematical foundations. So, all right. So today, so far we have discussed symmetric key, right? And we understand the concept of symmetric key that we use the same key, shared key, for encryption and decryption. All right. So message M is encrypted using shared key. Okay, it is a secret key also we call it. Okay, so shared session key. Sorry, we call it. So session keys means the keys used by both Alice and Bob, or two recipients, two people or two entities. Okay. And same key is used for encryption, decryption both ways, right? So if Alice wants to send a message, she will encrypt, send it to Bob. Bob will receive it and then decrypt it using same key, and reverse also, right? Bob sends something to Alice, uses a key for encryption, and the same key is used for decryption by Alice. Simple? All right. Now we are going to get into another important topic called asymmetric key exchange, or the asymmetric key encryption decryption. Okay. All right. So these are topics we'll cover. We'll start with symmetric key concept again. We'll see what are the issues, and then we'll come up to concept of key exchanges, and then we'll look at one algorithm called Diffie-Hellman exchange algorithm. All right. Symmetric key cryptography, by now, right? Because we have spent almost like 5-6 lectures on this topic. Okay. All right. So both Alice and Bob share a secret key, which we also call a session key. And the same key is used to encrypt and decrypt messages. Simple, and this is how most of the time in the history people have been doing. Same keys, older types, encrypted message will go to other party and then they know how to decrypt it. Right? So is inconvenient to see. This statement is not 100% correct because symmetric key is in use. It's a very efficient method. The encryption is very fast. Okay, and we use it heavily. So it is mostly use encryption technology, but there is some inconvenience in it, right? First thing is that both entities need to have the same key. Okay, that is inconvenience, right? How do you do it? If even in there, earlier when this symmetric encryption was used, and yeah, American army, they actually manually send the keys to entities, right? Actually, they used to have a very secure courier kind of service to send the keys. Now note that symmetric key works only between a pair. Did you notice it? Okay. So the only two entities can use. Suppose I want to communicate with a friend and the both of us will share the same key. But if I want to communicate with you, the whole each person in this class, so I will need 50 plus keys, right? Okay, of different people. So each pair will require a key. Okay. So there is a problem here, right? So first thing is that how do I send the keys to you? If I want to have symmetric encryption with each one of you, then how do I send the key? You are not in the same place. I can't go and manually give you a key. Then I have to take care of that key, and then make sure that it's not leaked. Yeah, but biggest problem is that number of keys I have to manage. So instead of communication with your class, suppose I have to communicate with everyone in institute, then of course my problem is bigger. I manage so many number of keys. Let's assume number of students plus staff put together is say 500. I need 500 keys. It's only me. How about you? You also need 500 keys. Okay, so this is not a convenient thing to do. So if there are n users, then we need n square, order n square keys, right? N into n minus 1 by 2 number of keys. And if n is large, this is very large number. Okay. So there's a first problem. First thing is creation of the keys, so many keys, and distribution of the key. Okay. And number of keys grows up. Okay. And so number of keys grows up is and is distribution. And also related problem is how do you keep it in your system. Okay. And very important is that it does not provide non-repudiation. So no protection against cheating by Alice or Bob. Okay, understand this issue? How does it happen? Anyone? We discussed this in last class, right? This is a knowledge of the keys with both Alice and Bob. And now Bob says that Alice has sent me something signed by or encrypted. Bob received encrypted message. Okay, example we have taken is that let's assume that Bob says Alice owes me, Alice promised me to give $1,000. But Alice says later, I have never sent you this. And both go to the court and can just say that yes, Alice, you need to give $1,000 to Bob. Can just say anyone?
No, sir.
Because Bob could create this message. Both have the same key, right? So non-repetition, proving non-repetition is not possible in symmetric encryption, right? So these are the issues. Okay. And then now we are into the internet age. Okay. Even here for this class, we are sitting in different parts of the country. How do I send you the key? Channel is insecure, right? Internet, for example, is insecure. Okay. How do I send you key? By manually or by internet or by mobile phone? There's a question. And each of these channel has insecurity, level of insecurity and inconvenience, right? So we have to solve this problem. And this problem is called key exchange problem. Okay. All right. All right. So basically it's something like this. Alice and Bob, they must agree on something which is a shared key. And for that, they need to send something to each other. And in between, we have Eve, who can see all this message is, yet she will not be able to derive shared key. So Eve can see everything. So Alice is sending something, Bob is sending something, Alice can see that. Okay, so Alice sends a key to Bob. Bob sends a key to some key, say key 1, key 2, to Alice, and Eve can see both key 1 and key 2. And then finally they agree on, say, key, common. So both can derive by exchange of message. Alice can derive key common, and Bob can also derive key common. But Eve cannot derive from key 1, key 2, key common. Is it possible? Yeah. Okay, this is the magic. This is how key exchanges work. Now let's see. All right. This is what we have discussed just now, that Eve in between can see everything, yet she should not be able to come out with the common key, right? Or shared secret key. So basically algorithm works in this way. Alice generates a private key and a public key. When we say private key, it means that is a secret key which is available only to Alice. So only Alice has access to this key. Okay, and she does not share private key with anybody else. Now public key that she generates, say she can declare to the world, this is my public key. So everyone knows the public key. Okay, similarly Bob has a private key and a public key, right? Now public key, Bob's public key is also visible to all. Now Alice and Bob then send their respective public key to each other. Okay, so in between, of course, when they say over insecure channel, then in between Eve can see those. Note that I am not using Mallory here, right? It's only Eve. Eve can only passively see everything and can do something, but she is not active in the sense that she is not man in the middle kind. Okay, she cannot change anything, she can just passively see. All right, now Bob has received Alice's public key and Alice has received Bob's public key. Okay, and then Alice then uses Bob's public key with her own private key to compute shared secret. And similarly, Bob uses his private key with Alice's public key to get the same shared secret. How is it possible? But Eve cannot get that shared secret, right? So there's the magic here. Okay, so it's something, this same thing described here in terms of photo diagram. It's a Bob's public key. Okay, so Alice is here, Bob is here. Alice uses her own private key and Bob's public key to get shared secret. Bob uses Alice's public key and his own private key to get shared secret. So basically what's happening, Alice generates private key which is known to her and public key. Similarly, Bob generates private key and public key. Okay, now Alice sends public key to Bob, Bob sends public key to Alice, Now Alice uses Bob's public key and her own private key to come out with shared secret or shared key. Okay, and similarly, similarly, Bob uses Alice's public key and his own private key to come out with the same thing. Both are same. Okay, so there is some mathematics in between. Now you can observe that there is some relationship between private key and public key. Okay, and this relationship is very interesting. Okay, and because of that, this magic is possible. So same thing pictorially. The man here is, oh sorry, Eve. I'm so sorry. Eve cannot, I mean, Alice says that here is my public key. Bob says here is my public key. Both send each other, send the key to each other, but Eve cannot find out this. Okay, because she is just she is passive. She is not active. She cannot manipulate these messages, but she can just read. Okay, if she is able to find out shared secret key, then whatever is being transmitted between Alice and Bob later, she can always find this out. Okay, here comes the Diffie-Hellman key exchange problem. It's not very old. It came out in 1976. So the goal of Diffie-Hellman is to create ephemeral key, which is ephemeral is basically a short-term key or where time span is very short, right? So basically we can create a key, use it for session and discard it. Okay, all right. So, and this technique is very useful in secure shell SSH that you would have studied or we will study later, how you would have heard, then TLS and IPsec. All these algorithms use this mechanism of key exchanges. Okay. Now let's take an analogy. Okay. It's given in, of course, this Berkeley book. You can read that. Suppose Alice and Bob shares a suppose Alice and Bob want a secret paint color, which is like shared key, right? Okay, but Eve can see paint color sent between Alice and Bob. So so Alice and Bob are sending paint colors. Okay, and Eve in between can see. Okay, and both of them need to agree on the same paint color. Okay, all right. Or there should be some algorithm which will say that now paint color between them is the same. Okay, so okay, all right. So we are here. So Alice generates a secret color amber, which we say A. Bob generates a secret color which is blue. Okay, and Alice and Bob agree on common public color green. Okay, now both have the common public color green, and now they both mix their secret colors with green. Okay, so as a result, what will happen? Alice mixes A amber with green and she will get amber green or green amber, GA. Bob mixes blue with amber, so he will get green. I'm so sorry. Bob mixes blue with green because green is common color, which is agreed, and it's also visible to Eve, right? So Bob will get green blue or GB. Is it clear till this point?
Yes, sir.
Okay. Now what is the next thing? Okay, next thing is that now this GA, Alice sends GA to Bob and Bob sends GB to Alice. So what's happening in between? Eve can see the following. She can see G because the public color. Okay, she can see GA, she can see GB. Okay, now what will happen next? Alice has got GB and Bob has got GA. Okay. So now Alice will mix A to received 1 GB. So this becomes then AGB, right? Or we call it GAB. Okay. This is what is there with Alice. And what Bob will have? Bob has received GA, and now he has color B. So he will have GAB. So Bob will have also GAB. Okay, so both have the same color, essentially same key. What Eve can do now? Okay, Eve knows G, Eve knows GA, Eve knows GB. Now she can form only green, amber, green, blue, GAGB, which is not the same as GAB. Got it?
Yes, sir.
Okay. Now here the trick is that she cannot separate out the colors. From, you know, if she, from GA that she sees, if she can separate out G and A, that she cannot. Then she can do, of course, her job, but it's not possible to remove them. Okay. All right. So from this color analogy, we can come out with some function. Now, of course, one thing is there that mixing two colors is easy, but separating them is impossible. Okay, so this is similar to one-way function, right? A function f such that given x is easy to compute fx, you know, but given value of fx, or that is y, then it's very difficult to get the value of x. So reversing, getting reverse, you know, reversing that, or from the answer, you know, y is the answer, getting into one of the arguments is impossible, right? Is, you know, one analogy you can see pictorially is that convert cow into hamburger, but impossible to convert hamburger into a cow. Of course, it's not a good example, but still is given in the book. Okay, so we come up with the one-way function, which is used in, which came out in Diffie-Hellman, or defined by Diffie-Hellman, which is fx. F is function of x, which is g, which is generator function. It could be, it's a public number, it's known to everyone, raised power x mod p. Okay, where p is large prime. You know what is prime number? Okay, and g is specially chosen generator. It's just a number. Okay, for example, right now you assume that it's just a positive integer number. Okay, so given x, now if we give you x and g is known, so finding out the value of g power x mod p is simple. You know, all of us know mod function, right? Okay.
Yes, sir.
All right. Now, given this, finding out value of x, if given this value, you solve this and is presented to you, and you know value of g and p, because these are public, finding out value of x is very difficult. Okay, this is the theory. Okay, now for that you have to go into modular mathematics. We'll not go into it, please read it through, but just it's also called group theory. Pause. Did you study this in your course? Modular or group theory? No? Yes or no? Yeah, I need answer. Either you studied or you have not studied it.
We know the basics, sir.
You know the basics. Okay. Okay. So please go through this. Okay, I will skip this. The important property of, okay, is something like this. Okay, when we say modular mathematics, essentially the numbers are within a group. Okay, or is a set of integers. So whole mathematics happens within that set of integers, right? Okay, these are positive integers. So for example, a clock, that clock that we use, numbers, while time keeps moving, okay, numbers are always between 1 and 12. Okay, so we can define a set and numbers, all the calculation, the result will be within that set. All right. Okay, so here we are used numbers between 1 and 12. Okay, similarly we can define a set which is modulo 5. So we have one elements of the set are 1, 2, 3, 4 and 0. Okay, similarly clock we can have either 1 to 12 or 0 to 11. Okay, and so on. Okay, so number always repeats within well-defined numbers, and so we say that is usually between 0 to p, or 1 to p, or 0 to p minus 1. Okay, all right. So, all right, and so we say modular anything, and of course this is a way to keep the numbers within limits. Okay, because multiplication, addition, all this results finally into numbers which are within that limit. Okay, so definition of modulus operation is that given a, r and m, where is m is greater than 0, okay, and then we say a is congruent to, or we use equivalent also. Okay, don't worry about it. A is congruent to r mod m. Sometimes you use a is equal to, or this sign, r mod m. Okay, and you know that, right? So what happens is that now r actually is remainder, and then r minus a should be visible by m. That's the condition. Okay, then we can write in this way. Now this can be, there is no unique value of r. That's normally we take the smallest one, but it could be, it can have many values. Similarly, a can have many values. Okay, all right, because it's a modulo function, right? So for example, here if a is 12 and m is 9, then then what is the value of r here would be, it could be any, and one possibility is that 9, okay, the value here 3 minus 12 should be, which is equal to minus 9, should be divisible by 9. So this is divisible by 9, so we get minus 1. Similarly, if a is 34, m is 9, we get 7 here, because 7 minus 34 is 27, minus 27 is divisible by 9, and so on. Similarly, minus 7 and 9 will get answer 2, because 2 minus 7 is 9, is divided in is divisible by 9, so you get, okay, all right. Okay, the remainder is not unique, as we discussed earlier, right? We can have multiple remainders. Okay, now note that a very important property is that all members of given equivalence class behave equivalently. Okay, so we can have multiple values of remainder for a given relationship, right? Okay, so all these behaves similarly. That's simple thing. And then we can always calculate inverse. Like we'll go back and see that so it will have property of closure, associativity, identity element. So they will define identity element, and then inverse element. So when we say inverse element, then a multiplied by a inverse equal to 1. So you'll have to find two elements in set. Okay, when they are multiplied, you get answer 1. with modulo relationship. Okay, so you can pictorially see here, if A and B are in this set, then AB will also be in the set. Okay, similarly associativity A into B into C is same as A into B into C, where A into B is, these are multiplied first into then and then multiplied with C, and then element A multiplied by unity element will always give the same element. And some most interesting is inverse element, that you'll have to find two elements in the set A and A inverse. When they are multiplied, they give the value of 1. Okay, so you'll have to think about how to do this. Okay, all right, so we'll not go further into detail. I will expect you to please read it by yourself. Okay, every book on almost every book you will find explanation of this theory. I will suggest you go through Christopher Parr's book. Christopher Parr's book is nice, very nicely written. Okay, all right. Okay, so modular division, you can also learn about it. B is a B by A, B divided by A. We can write it B into or multiplied with A inverse, and then you'll have to find out what is A inverse. By this equation, A into A inverse is 1 mod M. Note that when we do inverse, you'll have to always have relationship with M. So for example, you do 5 by 7 mod 9. Okay, so basically we'll have to find out inverse of 7 mod 9. Okay, so inverse of 7 mod 9 is 4. Okay, so you get 7 into, because 7 to 4 is 28, and when you do mod with 9, so 28 mod 9 is equal to 1. Okay, so 5 by 7 mod 9, if you solve this and inverse of 7 you got 1, inverse of 7 you got 4. Okay, so your answer is that it's a 20 mod 9, which is equivalent to 2 mod 9. Okay, so please, I'm requesting you to please read this. I know I'm just moving very fast here, but it's not really that we can cover all this, right? Given limited time we have for this, this chapter. Okay, all right. Now, so Diffie-Hellman algorithm relies on discrete algorithm problem. Okay. Right? So this value of G is given to us, okay, which is say 3 here. Okay, now given you this thing 2, 5 and 3, can you find uniquely the value of X? In this equation, it is comparatively simpler because you can do it manually. It is X equal to 3. But if this P, which is 5, becomes big, say 256 digit or bits, then finding out X is impossible. Okay, so I will request, and there's no known algorithm for that. So please manually do some problems. Try doing it manually and you'll see the difficulty. Okay, and this is the main thing in Diffie-Hellman algorithm. It's called discrete logarithmic problem. It's based on discrete logarithmic problem. Now, okay, let's come to Diffie-Hellman key exchange. So private key, Alice has private key A, Bob has private key private key. This Bob. Bob has private key B, A and B. Okay. And now from this, they generate, Alice generates public key A and Bob generates public key B. So note we have said that there is a relationship between public key and private key, and then private key is known only to respective person. Okay. So now Alice generates public key A, which is G raised power A mod P. Okay, Bob, similarly, Bob generates public key B is equal to G raised power mod P. Okay. And now Alice receives Bob's public key B and Bob receives Alice's public key A. Okay. From received key B, Alice can compute B raised power A mod P because B is given to Alice. It comes from Bob. A she knows because A is her secret key, and mod function she knows, and P is also known to everyone. Okay. So now from this she can calculate in this way. B is known, so this value she can easily calculate, which is equivalent to, now she can calculate this because B is known, value of B is known. Now you derive it further, then you can find out that B is nothing but G raised power B, this one, and then she does A raised power A, so B raised power A, it becomes G raised power B raised power A mod P, which becomes G raised power AB mod P. Similarly, Bob receives public key A. This Bob receives as a number, and then he does B is his own private key, which he knows. So he can always do A raised power mod P, which actually is, by this derivation, will say that is G raised power A B mod P. So now it means that now these two are same, means that now both of them have the same key. Okay, any catch here? Are you able to understand?
Yes, sir.
Okay, think about it. It doesn't. Please go through modular arithmetics, and if you really want to go into details of that. Okay. Now, what will happen to Eve? What Eve has received? Eve has received both A and B. Okay, there's capital A and capital B. What can she get out of that? If she combines these two, if she multiplies these two, she will get G raised power A plus B mod P. Okay. Now this is not same as G raised power AB. All right, so that's the trick. Okay, so formally we can define it as follows. Now generator G is known and large prime P is known. So we can say discrete algorithm problem is given G raised power A mod P, it is computationally hard to find A. Okay, and then from this Diffie-Hellman problem is that given this one G raised power A mod P and G raised power B mod P, it is computationally hard to find G raised power AB mod P for anybody in between like Eve. Okay, all right. Okay. Obviously, this point we already discussed. G raised power A plus B mod P is not same as G raised power AB mod P. Okay. So now that we can define algorithm. P is a log. So now these two parameters P and G, okay, are public parameters. It's known to everyone. Okay. So when we look at Diffie-Hellman algorithm, which is available as a library, Everyone uses those number P and G. These well published numbers, right? So P is a large prime and G is a generator function. Now here it says that we'll have to choose a value of G between 1, which is greater than 1, that's actually 2, and less than P minus 1. Okay. So Alice could pick up P and G and then announce it publicly to Bob. Let's assume that the announcement happened. Normally it's known to everyone. Okay, so today P and G are often hard coded or defined by a standard. It means that P and G value, P is a number, it's a large prime, and then G is based on that within some range. Okay, these are known to everyone. Then Alice calculates, now Alice picks up A between 0 and P minus 2, which is, that's her, A is her secret key, right, or private key. And then she computes G raised power A mod P, that she computes A. Okay, so A is her public key. Okay, and Bob does similarly, he picks up random. Note that is a word random, right? A value of B. Similarly, A is a random value between in this range. So similarly, Bob picks up a random value B in this range. Okay, it means that any of these numbers have equal probability here when we use word random. And then compute B. Okay, so private, this is private key, and then B is public key. Now, to anybody he wants to communicate, he can share his public key. Okay, his public key and receive that person's public key, and then both of them can calculate a common session key. Okay, all right. So this is the algorithm. So you can now go through a simple example. Now this of course is a, I'm sorry, this again algorithm defined, same thing, right? Accepting that here E, what E will get is nothing but G raised power A plus B mod P. So that point we have already discussed. Okay. And then there is a calculation how much time algorithm will take. The fastest known algorithm for solving this problem takes this time 2 raised power Cn raised power of 1 by 3 log n raised power 2 by 3 and so on. So if P is a n bit prime, okay. Okay, so now if we'll have to take large value of n is the number of bits in P, right? The number of bits in, so if take very large value of n, it is algorithm is too slow to allow reasonable attacks. Okay, pictorially we can define this as follows: Alice generates A, Bob generates B. These are the private keys. The private key. From this, from A, which is private key, she uses this function to generate public key. Similarly, Bob generates public key, and they exchange this. So what G raised power A mod P exchange here. So Bob receives Alice's public key, G raised power mod P, and Alice receives Bob's public key. And then Alice knows her private key, which is A, and she does this calculation, G raised power. So this she receives B. So B raised power A mod P, and now finally she gets G raised power AB, and similarly Bob gets G raised power B, while Eve receiving G raised power and G raised power B cannot get G raised power AB. Okay, so this is a simple calculation. So of course, as we discussed, we can use this for communication among multiple parties, as long as other party is public key and that person knows your public key, you're done. Now, one question, of course, you can always ask is that how public keys are announced. Okay, so you can Google it and see that for most of the websites or important websites, etc., probably public keys are announced. Okay, other way, can somebody manipulate public key? So instead of if we have Mallory, and when Alice sends public key to Bob, Mallory can always change it. So active attacks, even with this algorithm, are possible. Okay, we will discuss later. Okay, right now let's not worry about active attacks. Now what we are looking at is just somebody passively observes, cannot create the shared secret key. All right. Look at this example, is a toy example. I'm sorry, this already we have discussed. This is summary of the algorithm. Please go through it again. It's the same thing. Okay. Do this exercise at home. Take P is 11, G is equal to 2, hard compute with pencil and paper, and see what are the, you can guess the value of X. You hard compute it, right? You can use calculator also. Okay. Now, what is ephemerality of Diffie-Hellman? What is ephemeral? Ephemeral is something which is short term and temporary, not permanent, right? So basically this algorithm can be used, but there is a timeline, because in order to avoid various kind of attacks. Okay. Ephemeral is called because as we discussed, keys can be shared, keys can be used, or public private key can be used only for short duration. Hence, the algorithm is called Diffie-Hellman ephemeral, DHE. Okay, it means that both Bob and Alice discards A, B. Alice will discard A, Bob will discard B, and then public key when they are done with communication. Okay, and this provides forward secrecy. Right? So forward secrecy is when somebody cannot guess in future. Okay, okay. Go through it. Okay, is it becoming clear? What we have discussed so far? So, we have discussed too many things. Okay. All right. So we started with, we have seen that in case of symmetric key, it is very hard to communicate keys among multiple parties. Now, if just two people, is possibly it can be done over phone or something. But I mean, even over phone, if you have to describe somebody, 1000-bit keys is hard. Okay. So in general, it's hard that two parties have the same key in normal practice, right? And if number of pairs is high, number of people who want to communicate, then number of keys that is to be generated is very large, order n square. So it's very difficult problem to solve. Okay, a simple way of it cannot be done manually, it cannot be done just plain over internet, okay, by sharing, right? So now simple solution of is that use key exchange algorithm, okay, where they try to a pair of users, Bob and Alice, communicate with each other their private public keys, and from the public key of other party they come out with a secret session key. Okay, that's the basic, and then we came up with Diffie-Hellman algorithm, okay, which is used in secured shell, TLS and IPsec. Will study all three. Okay, and we have looked at this example. And then we looked at some basic modular arithmetic, which you will have to go through the book. Of course, I didn't cover it fully. Okay, and then we come out with this discrete logarithmic problem, wherein we have we define a function like this, this, and we say that given value of a, given value of p, given value of g, it is impossible to find value of a. So this a becomes public key, p is a function known, g it is a generator function which is also known, a is very difficult to find, impossible to find, right? Okay, all right. So now all right, so that's all we have seen that Alice generates private key, Bob generates private key, and then Bob also generates public key. And note that there is a relationship between the two. Now this relationship is in a very intricate manner that we cannot, if Eve cannot find out many details until she knows A, and now A is secret. Okay, so now public key, Bob, and once they generate their private public key, they exchange public key, and from that public key, combination of public key and the private key of the person, public key of another party and private key of oneself, common shared secret like G raised power p can be calculated. Okay, so that's all. And please go through it, because we will use this again and again in when we study basically security in networking protocol. Okay, all right. So now next we will cover is L-gamma encryption, and then we'll cover RSA algorithm, then we'll cover digital signatures, and then move on to networking, security in networks. Okay, all right. Any question?
No, sir.
All right, thank you. Please read from the book, because this very important, very magical algorithm, and it has changed the world of cryptography. It has changed the world of earlier only symmetric encryption was used. Now asymmetric encryption, like Diffie Hellman algorithm, is very, very important, that you can over insecure channel by communicating public keys, you can create a session key. All right. Okay, bye.